Continuing on from the previous video, just to review the results that we got. So we got, a system with three modes, and those three modes were associated with each of these three eigenvalues. Now, two of these eigenvalues are real, whereas one is a pair of complex conjugates. And we said that this is a first order mode, this is this is another first order mode, and this is a second order mode. And then we found out some of the transient response characteristics. Let me try and draw these responses in conjunction with each other, like next to each other, and see what happens. Now, I'm going to draw them on the same scale. It doesn't mean that they all have the same steady state value, because those values depend on the weights, and we'll have to work out the transfer function and the impulse response, step response based on that transfer function to work out the weights. But then qualitatively, this is what the responses look like. Okay, so first one is over here, this one, the first order mode, which looks something like this. Now that has a settling time, I think we figured out, of about 0.68 something seconds, 0.689 seconds or something. The second one is another first order mode, this one. Now that had a slightly higher settling time, so it looks something like this, around 1.03 seconds. And the third one, the second order mode over here, that had a very large settling time. In fact, if you remember, its peak overshoot was something like over here. 1.4 seconds was peak overshoot time. So this mode is extremely slow. So it looks something like this. And it's going to go out of the frame of this picture. So it's going to settle over a very long period of time. So settling time was 25 something seconds, which is very large. So that's the dominant mode, like I mentioned in the previous video as well. So this is the dominant mode. So after about 1 second, after about after about 1 second, you're going to find that most of the system's response is going to be dominated by this guy, by the green mode. Okay, so even before we find out what exactly happens to these modes, right, we are confident that we have understood something about its transient response characteristics. And now if you want to find out the exact way in which the response looks like, that's when we have to worry about the transfer function and or the B matrix. So remember, we got this far without actually worrying about the B matrix at all. So we got these numbers, the eigenvalues, and all of the settling times and rise times and peak overshoot, everything. We got them just based on the A matrix. We never needed to find out what the B matrix looks like. And that's something you should remember. Now, if you want to find out what the total response looks like, how to add up these three in what proportions, that's something where the B matrix does come in, and we'll have to talk about that. So there are two things that I'll want to do in terms of details. One detail is calculating the actual impulse response, and to this end we actually use the MATLAB's impulse function. And I'm not going to work out impulse and or step function. And I'm not going to work out the entire Laplace inverse or whatever, but I'm just going to show you the steps so you understand the way in which these three modes are combined to give you the response of the overall system, whether it's the step or the impulse. So that's one part. The other part is some details about the second order mode itself. Okay, so remember when we talked about the second order mode, I introduced something like a standard form, which had the zeta, omega n, and so on. Now, I didn't really use it here, But those that standard form is actually very important because it tells you something about second order systems in general just by looking at those numbers even before you work out any of these characteristics. So those are the two main things that I'd like to talk about in terms of details about transient response. So, continuing on further, let's look at the overall step response, and the impulse response is pretty much the same, and see how it relates to those individual modes. So, this is something I alluded to in class, and just let's make that explicit now. So, if you look at the transfer function, so step one here is to find the transfer function, and here we have 4 states and 1 input, so you'll have 4 transfer functions, but we are interested in what happens to the first state. Okay, now this is again another detail. Now when we did the previous analysis, I didn't even mention which state we are interested in because the modes apply to all the states, so they're going to show up everywhere. Now in what combination they are added together, that's the thing that differs when we consider one state or the other. But this is something that was a part of your homework previously. So we had the transfer function of the first state from the sole input, single input. And if you work this out, we did this with MATLAB, this works out to something like this for these numbers. It works out to around 50s plus 100 over s to the fourth plus 10s cubed plus 30s squared plus 50s plus 100. Okay, so that's what it works out to. I did this using MATLAB, I didn't calculate it by hand. So if we were to calculate the step response, what we'd have to do is bring this u over to this side and then work out the Laplace inverse of this guy. So let's do that on the next slide. So this is what we need to do. Like I said, let's write out the state, the desired state in terms of the transfer function multiplied by u of s, which is this. And if I'm interested in a step response, the u of s is 1 over s. So that's what I'm going to do. U of s is 1 over s. So all I have to do then is figure out the inverse Laplace transform of this whole right hand side. So I have x1 of t as the inverse Laplace of x1 of s, which is 50s plus 100, now multiplied by 1 over s, which comes from the u of s, by the same denominator. And the way to find this Laplace inverse is to do the partial fraction expansion. And like I said before, I'm not actually going to work out the whole thing, but I'd just like to show you what form it takes. Partial fraction expansion, which will work out to something like this. It will work out to some constant, or some numerator, I should say, some numerator divided by s plus some other numerator divided by now the first order mode, which was 5.803. So I'll get that. Then the another first order mode, which was 3.8844. And then I have the second order mode. So I'll have s squared plus I think I should get something like 0.3116 s plus 4.4343. And you'll notice that if I try to factorize this quadratic or try to take the roots of this quadratic, they won't work out to real numbers. So those will be the complex conjugates. So again, you should see the same structure here. So this is the first order, the two first order modes. Exact same thing as before, but now in transfer function form, and this is the second order mode. Okay, so all I did was if you factorize this fourth order polynomial, you get these factors. And how do I know that? Well, that's because the eigenvalues of the A matrix must be the same as the roots of this polynomial, right? So that's something we have established before. And that brings me to one terminology that's super important. The roots of this polynomial, this big polynomial, are what are called poles. Roots of this polynomial are called poles. They're the exact same as the eigenvalues of the A matrix. There is no difference. It is just two different theoretical approaches. One was developed back in the 1920s, which is this transfer function approach, and the other, which is the matrix approach, the A matrix approach, that was developed in the 1960s. They talk about the exact same system, so it's not surprising that you should get some exact same numbers. And those are the numbers. So the poles are equal to the eigenvalues. Okay, so the roots of the denominator are the eigenvalues, and those poles show up here. So this is a pole, minus 5.803 is a pole, minus 3.884 is a pole, and whatever are the complex roots of this polynomial, those are two more poles. So as many poles as eigenvalues. So they are identical. Poles are the same as eigenvalues of the A matrix. So just to reiterate on a clean slide, this is our step response of x, which is really two things. One is the transfer function, and the second is the Laplace transform of the input. So that's here, and the transfer function is here. And just by way of terminology, the roots of the denominator of the transfer function here, they're called poles, and they're the exact same as the eigenvalues of the A matrix, which we calculated before, and they will show up in the partial fraction expansion. Another way of terminology, you'll see that the numerator in this case now is also a polynomial. In this case, the numerator is also a polynomial. Previously, we'd seen a bunch of numerators with constants in them, and now this is probably the first example where we have seen a polynomial. So this is a linear polynomial, 50s plus 100. So the roots of the numerator of g of s are called zeros. And they also affect the transient response in some ways, which we won't have the time to study in a lot of detail, but that's something you should be aware of. So these are called zeros, and they don't immediately show up in the A matrix. So there is no one-to-one correlation of the zeros to something in the A matrix, but that's something that crops up. Now the other thing that happens is, because our numerator has a s in it, in the partial fraction expansion, so let me just write out the partial fraction expansion one more time over here. So this will look like something along the lines of c1 over s plus c2 over s plus 5.8 or whatever that was, 5.80 I think, 803 plus C4 over S plus 3.884 plus the second order term. I think I missed a C somewhere. Okay. So this will be a second order term, S squared plus 0.3116 S plus 4.34 or 4.434. Now, the thing to notice is that because the numerator over here has an S in it, has an S and a constant, we should expect from the partial fraction expansion that some or more of one or more of these C's, the numerator C's, will also have an S in it. Okay, and that's something you might have studied when you did partial fraction expansions of Laplace transforms. I'm not going to beat on it too much right now, but the only thing that I want to point out is that these guys, these C1, C2, C3, C4, these may be polynomials of S, especially linear polynomials of S in this case, and they play a role in the way these four or these three modes and this input U of S add up to give you the overall step response of the system. Okay, so the overall response is going to look different from each of these three modes that we saw. It's going to be a weighted sum, as you can see there. You essentially add up, but the adding up happens with some weighting terms. So these are weighting terms over here, and the way this partial fraction works out will affect the way these modes are added up. So that's all I wanted to point out qualitatively. I don't want to actually sit and calculate that. The one thing that we do have to calculate is what's called the steady state value of the overall response, which we'll do on the next slide. So by steady state value, here's what I mean. We've already established by looking at the eigenvalues that this system is stable, right? So what's happening is you have an input U and you have an output, which in our case we decided was x1, and we are trying to find out what happens if this is a step right here at the input. So let me use a different color to say this is a step. We're trying to find out what happens at the output, and that's the step response. And we have established more or less that it's going to have some exponential decay characteristics and some oscillatory characteristics. So the response overall is going to look like this, something like that. Okay, and the only reason I drew oscillations was we established, that the dominant mode is second order, so the first order modes do exist here, but they're going to die off pretty soon. Anyways, so it's going to settle to some value. Now we'd like to know after it settles. So this is the transient. Okay, so the transient was this period, and we found that the settling time of the second order mode was 25 something seconds, which means that and the two first order modes had a much lower settling time, which means that after this time, after about 25 seconds, everything settles down. There are no more changes. So that's when we say the transient period is over and we have a steady state period. So this is the steady state period, which is forever unless something else happens. So we'd like to find out what happens in a steady state, and the only thing of interest is how much is this value. So when the response settles down, to what value does it settle? Now remember, we have a step input here, so this value is 1. Okay, this value is 1. So we'd like to find out if this is 1 as well. So that's the question of interest. Is this also 1, or does it settle to something other than 1? Because remember, now if you're trying to make your system follow the input, so we have this differential drive example, right? So in that case, if you give it a step input, it means that you're trying to make the output follow whatever value you give at the input. So it is in our interest to make this value over here the same as this value, or at least we should know what value this takes before we try to make it the same or not, which depends on the application. So we'd like to find out if this is 1. And I gave you the entire expression for the step response, and now we can just look up the MATLAB step response function. So one way to find out is just use step in MATLAB, right? So step will tell you the answer to this question of what the steady state value is. But there's a much easier way, and the easier way depends on what's called the final value theorem, which you may have studied when you studied Laplace transforms. And the final value theorem says that in this case the value of x1 at infinity, which is the steady state value, okay, at time t equals infinity. Now this is small x1, so this is small x1, which is the time domain value of it, is equal to the limit as s tends to 0. So there is something in the frequency domain that we can calculate to figure out the steady state time domain value. So this is s times x1 of s. Evaluate the limit as s tends to 0 of s times x1 of s, and you get the steady state value. So in this case it's particularly easy, right? In this case, if we work out s times x1 of s works out to 50s plus 100, or actually the limit is that tends to 0. The limit is that tends to 0. 50s plus 100 over that whole mess, which I'm not going to write out again. And you'll see immediately that this limit is easy to work out, and it just works out to 1. So you'll get a 100 divided by 100, and this s cancels out because of this s. So this s over here cancels out this s over here, and it's in the limit, so we can cancel it out without worrying about dividing 0 by 0 or anything. And that's what we get. So in the limit, then all we have to do is just set all of these guys to 0, and you get 100 divided by 100, so that's equal to 1. So here in this specific example, we have verified that the steady state value of x1 does in fact go to the same as the input. So there is no difference in the steady state value from the step, and that's something that will be of interest to us when we're trying to, for example, a tracking application. So if you're trying to make your differential drive as before follow a wall, it needs to settle to the right value, and that's something that we need to establish. So that's the new thing that we have established today, the steady state value.